Hey everybody, welcome to Systems Expert. Let's dive into the question.
Hey Clement. So for this systems design interview, I want you to design a global and fast code deployment system.
A global and fast code deployment system. Okay, so from past experience with code deployment systems, a code deployment system can have a few different things going on. First of all, a code deployment system might involve like building code into binaries, like pieces of data, the compiled code. It might involve testing code. These two things might happen when you're submitting code for code review, when you are actually merging that code into some central code base, when you're in the process of deploying the code. So my question is, what part of the deployment pipeline are we actually building here? Are we doing both building and testing? Are we doing something else?
Right. So I'd like you to design a system that takes the code,
Okay.
builds it into a binary, as you said,
Okay.
and deploys the result globally in an efficient way and in a way that's also scalable. But that being said, I don't want you to worry about any of the testing for this code. We can assume that's already covered.
Okay. And just to clarify again, what part of the software development lifecycle, so to speak, is this happening at? Like, is this when code has been merged into the central code base, or?
Yeah. So once the code is merged to either in the master branch or the trunk of the repository, we want engineers to be able to, like through a UI or a CLI, we want them to be able to trigger a build and then trigger a deployment for that build. And so the code, you can assume, is already reviewed and ready to ship to production. But so to clarify, you're not designing the system that handles submitting code and reviewing that code.
Okay. So basically, what we're doing is we're taking code that is presumably shippable, and we are trying to ship it to production by sending it to all of our application servers around the world.
Yeah,
Okay.
that's exactly it.
Okay, so let me write that down actually. Let me write these two things down. We are number one, building code. So I'll write this down here, building code. And then number two, we are deploying that code.
Okay.
So deploying that code. I guess my next question has to do with what you just said, or what I just hinted at here, the global thing, the global aspect of this system. Are we, like, the machines that we are deploying this code to, are they located all over the world, or are they located only in some parts of the world, or?
Right. So I'd like you to design a system that scales to the entire world. But so for, I guess, simplicity's sake, we can just assume there's 5 or 10 different regions with hundreds of thousands of machines spread out throughout those 5 or 10 regions.
Okay. So I'll put 5 to 10 regions
Yeah.
globally, and you said that they can be basically spread out across the world.
Mm-hmm.
And then we have hundreds of thousands. Okay, so 100Ks of machines that we're deploying this code to. Okay. And I guess this is an internal system because we're doing this on behalf of the company or of the engineers, right?
Yeah. So it is an internal system. Only
Does,
the engineers that are deploying the code will actually be interacting with it.
okay. Does that mean that as far as availability is concerned, like are we okay with failures in the deployments? How long do we want these deployments to take? And the reason I'm asking this is because, like, when we deal with internal systems, sometimes we're okay with a little bit less availability than external systems, but I just want to make sure.
Right. So even though it's an internal system, this is kind of a special case as far as they go.
Okay.
We still want to have decent availability specifically because a lot of outages in large companies, most outages I would even say, are resolved by fixing the bug and rolling forward or rolling back a particular deployment.
Okay.
And so that the system that you're designing has to be available in order to kind of be used as a response to certain outages.
Okay.
And then in terms of the build pipeline, I'd like every build to eventually reach a terminal state, so either failed or succeeded. And then once, in terms of timing, once a build is done, we want that to be shippable to all machines within 30 minutes.
Okay, within 30 minutes. So just to clarify, with regards to the availability, are we still okay with something like 2 to 3 nines of availability, meaning anywhere between half a day and 3 days of downtime per year? Or are we shooting for something a little bit more extreme, like a highly available system, truly?
For this question, let's just say 2 to 3 nines is perfectly fine.
Okay. Okay, then the reason I'm asking this just is because I want to make sure to know if I have to optimize for that. Well, I guess we'll see when we get into the actual implementation of the design, but I'll write that down then. 2 to 3 nines of availability, and we said 30 minutes. 30 minutes for a deploy, and here just to confirm, it's basically the entire process of taking code, building it into a binary, and deploying it to the hundreds of thousands of machines across the 10 regions. That should take 30 minutes.
Yeah, let's say that. Yep.
Okay, so 30 minutes for the entire deployment. I'll just write deploy. And I guess the final couple of questions that I have here are, how often are we going to be deploying code, and how big are these binaries that we're going to be getting? How big are they going to be? Like, what's the biggest size we could have for one?
Right. So you can imagine at a large company, you're going to have a lot of different engineering teams working on, say, hundreds of different services or web applications. And they'll be building and deploying things in total thousands of times a day. And the final builds, depending on what it is, could reach up to 10 gigabytes for this particular system.
Okay.
However, so that being said, I don't want you to worry about what language these apps are written in or how they're compiled. You can just assume that the internal process for building a binary is kind of taken care of. And your whole system can be agnostic to the specific technology that you're building.
I see. Okay, so that actually simplifies part of the building of the binaries a little bit.
Yeah.
But you said we are going to be deploying, though, 10,000 times per day, or thousands of times per day, you said?
Yeah.
So I'll put thousands of deploys per day. And by the way, when I say deploy, I'm really also counting the building of the code. And then you said that we might have files that are up to 10 gigabytes. Okay, so 10 gigabytes per file, or per binary, let's say. Okay, so I think I have a general idea of what system we're designing here. What I've written down basically are the main system requirements or system restrictions that I'm thinking about. And to be honest, I think that we can design this system in two main parts, because the two things that we mentioned at the beginning, building code and deploying code, these actually seem like the two clear parts of the system, the two subsystems of the system. So I'm actually thinking of approaching this problem like that, by first designing the system to build the code, and then designing the system to deploy the code. Does that seem like a sensible strategy?
Yeah.
Okay.
So let's get to part one, building code.
Okay. So I'm trying to think. First of all, to maybe, I guess this is one more question I should ask. Trying to get a clearer sense of how this system is gonna actually flow. Is the idea that engineers write code, they commit code to the code base, right? So you have a commit that might have like a SHA or something that points to it. And these commits, once they get merged into master, are the commits that we're going to use to actually, build into binaries. Is that the idea?
Yeah. So you can refer to a specific version of the code that you're building through the SHA of the commit for that code.
Perfect. So then I think that makes sense. And I think then the idea that I have for building the code is some kind of queuing mechanism, right? Where you have commits, commits that come in as engineers are pushing code up and merging it into the master branch. And as these commits come in, you create what I'm going to call like jobs, right? A job of
Okay.
building the code out of the commit and or building the binary rather. And the idea is, yeah, you queue these jobs one after the other, and then you've got a set of servers, which I like to call like workers, a pool of workers that are going to take these jobs off the queue. I guess in a queue like
Okay.
fashion, first in, first out. Like the first commit to get into the queue is going to be the first job, or is going to have the first job related to it that builds the code that gets taken by some server, and that gets run, that gets built into a binary, and then you have the binary. Does this kind of make sense?
Yeah, but so where once that binary is built on the worker,
Yeah.
like do you just leave it there? Like what are you
No,
expecting to do with it?
no. The idea would be like once you've got a binary that's built, you store it into storage, and I guess you probably want these binaries. Yeah, you're going to want these binaries for a long time, if not forever. So you store them in storage. I'm thinking a blob store like Google Cloud Storage (GCS) would be good because a binary is just like this opaque blob of data. I think it's
Yeah.
just very sensible a database for that. But yeah, you would basically store the binary in a blob store.
Okay. So that's for final storage.
Yep.
Now I do have another question about your queue. So I think a queue makes perfect sense because it should be kind of first come first served. If possible, someone who triggers a build first should get it running first. But that being said, how do you plan on implementing the queue itself? What is backing that like queue data structure that you're talking about?
Yeah. So I guess just to get a clearer picture of what I'm doing here, because I've got an idea that's popping in my mind, but I'm not sure if it's maybe a little bit too trivial or too naive. But let me just write down this system. So give myself a bit of space. We've got this queue here, right? And I'll draw this as a directed arrow for the sake of the example. But you've got this queue, then you've got a bunch of servers, right, that take jobs off the queue. And
Okay.
these servers then, run these jobs. They build the code into binaries, and then they store the binaries into, let's say, one blob store, which is going to be GCS, Google Cloud Storage, just because I'm familiar with this one. That would be the system. Now, how the queue is structured or is implemented, rather, I guess like the idea that comes to mind at first is just to do this very simply, implement a queue just as you would in actual code, like in a coding interview, for instance. You have a data structure that you store in memory on some server, and you have your jobs stored in that queue in memory. The only thing about that is that, like, if your server goes down, you lose all of the state for all of your jobs. And from past experience with code deployment systems, typically you want to have all historical builds or jobs, like what their status is. You don't want to lose
Yeah.
that state, right?
Let me actually add that as a requirement.
Okay.
We do want to persist kind of the historical statuses of all the builds that we've
Okay.
had for potentially a very long time. So memory is definitely not the kind of medium we want for that.
Okay. So then, in that case, this makes sense, and it confirms the doubts that I had, and the idea of like trying to optimize this in memory queue structure seems not correct. So I'm thinking that we might be able to use a SQL database for the queue because we want persistent storage. We want that queue or the past jobs to always be there. And I'm
Okay.
thinking a SQL database. If you take a SQL table, right, a table could actually be our queue. Like the table could represent our
Okay.
queue, where every job is stored in that table. So every record or every row in the table is a job, and you would take jobs off the queue by looking at the table and doing some sort of logic to find which one should be dequeued next. Does that
Okay.
make sense?
Um, Yeah, so let's dive a little deeper in
Okay.
that SQL queue. Can you give me an idea as to what the table will actually look like, what columns that table would have, and as well as what each column would represent and how you use these in a DQ operation?
Sure. Yeah. So I guess here, if we take our little design up here where we've got the queue, you've got servers or workers that are taking stuff off the queue and storing in GCS. Maybe, by the way, I'll add just a few arrows here to show that they're storing the binaries in GCS. But
Okay.
if we zoom into this queue, this is actually a SQL database or a SQL, and specifically it's a table, an actual table. And I'll give myself a bit of space here to make it pretty large. This table would be called, let's say, jobs,
Okay.
because it stores all of the jobs. Maybe it could be called like job queue. And the idea is, let's see, we would have, what types of columns will we have? Because we want to store the name of the, well, we want some name for the job, right? This might be like the some auto generated ID. That would be maybe the
Okay.
first column. So let me actually write that down. Let me start writing that down. We have a big column here that's got a bunch of, or a big table, sorry, that's got a bunch of columns, and the every row is a job. The first one is ID. This is the job name. This is some arbitrary name. Then we've got, I guess we are creating binaries out of these jobs, right? So we need these
Yeah.
binaries to be referenceable, and we need these binaries, I think, we're going to store them in GCS, so they're going to have a name. So we'll have a name here for the binaries, and this might be something that we specifically like create based on some pattern,
Okay.
or some rules that we might have. The next thing that we want is, we're definitely going to want a, like the time at which the job was created, and this would be
Yeah.
based off of, like, if we want to design our system such that it pulls any commit that has been like or it creates a job out of any commit that has just been merged in the master branch, then we could have a commit SHA stored in one column, and we could have the creation time or created at time, a timestamp in in another column that would be basically the
Okay.
time when that code was submitted to the master branch. Does that make
Okay.
sense? Okay.
Yeah, or the time at which the build was or the build was enqueued, right?
Yes, or the time when the build was
Yeah.
enqueued. And so I guess
Cool.
here the idea would be, we would put commit SHA. I'll just write SHA, and here
Okay.
then I would put created at, and this would be a timestamp in SQL. Um, and
Okay.
then the final column, because we do need another column, which might be the most important one, would be the status of the jobs, because we're dealing with these jobs that have. Let me think. We're trying to create binaries out of code, and at the beginning you said we want a clear end state, right? You said we want to know if a job or if code has been successfully built
Yeah.
or unsuccessfully built.
Yeah. Yeah. Yeah.
So yeah, we basically need a status. So I'm gonna put this here as a status, and I
Okay.
think this should be like an enum where we can have uh, succeeded, we can have failed, we can have. I guess we would need to have running to know if the job is running, and this would be for our servers, our workers, to know if they have to, like, can they DQ this job, right?
Okay.
If
Because
it's
if it's
running,
running,
yeah, they don't want to
yeah.
DQ it. And
Okay.
then finally there would be a queued status. Like, is the job like there available but not running, and certainly not succeeded or failed. And I guess, like,
Okay.
are there any
I
other
mean,
statuses?
there's one operation that's pretty useful in a real life system. It's like if you want to cancel a particular build, that might be useful. But
Okay.
and we might have a status added to the enum called like canceled or something. But I don't want you to worry about this flow. Not in this question. So
Okay.
just assume the list of statuses that you have is sufficient.
Okay. And I think, like, we could add that if we wanted to, right? It would
Yeah.
be fairly simple given this structure of this table.
Hmm.
But I think what's nice about using SQL, the more that I think of it, looking at this table, is that we not only have the queue very clearly structured here. We've got this table of jobs, right? But
Hmm.
they like the queue mechanism comes to fruition, so to speak, once you look at the created at, or whoops, let me point to that, the created at column and the status column, right? If a
Okay.
let's see, if a job is queued, not running, not succeeded, not failed, but queued, and has the oldest created at timestamp, meaning is the first job, the first queued job of all of the stored queued jobs to have been added to the queue, to the table,
Sure.
then
Yeah.
that's the next one that we want one of our workers to take DQ and start building.
Okay. Yeah, that makes sense. But so, given the fact that you're going to have multiple workers, do you like how do you plan on having this queued data structure be, I guess, concurrency safe, or is your solution right now to use SQL good given the concurrency that we'll have?
Well, I think that it is good because if we are, yeah, because you're saying basically you have, let's say, 100 workers at once. And I guess
Right.
we'll try to estimate maybe a bit later like how many workers we would need. But let's say we have 100 workers that are all looking for a job to DQ and to start building in this database. The fact that it's a SQL database, maybe I'll write this down. The fact that this is a SQL database and that it would basically have ACID transactions. ACID transactions are key here. ACID transactions are going to be key to having our hundreds of workers be able to, you know, go into this database and perform updates or reads in this database all at once without worrying about concurrency issues because the transactions would be executed as if they were sequential and there would be no like problems there. If you want, like,
Cool.
maybe I should
Yeah.
explain like my concept, like how I'm thinking of this to work from a transactional point of view, right? The idea is you have like
Y- like how you would write the SQL query, you mean?
yes, exactly. Like how I would, yeah,
Okay.
how I would write the SQL query.
So sure. Yeah. Yeah.
So, do you want? Would we like me to actually write the SQL query, or just say it out loud?
Yeah.
Or
So yeah, if you could write it, that'd be great.
okay,
I'm not like syntax mistakes are fine. I just
okay,
want to get an idea of the basics.
sure. Okay, so just to clarify, my idea is the way that these workers actually DQ stuff off the queue or out of the table, so to speak. They take jobs out of the table. They don't actually take them out of the table. They don't delete them from the table, but they take them from the table. Is with transactions, and the idea would be the a single worker performs a transaction that gets all of the all of the jobs that are currently queued, meaning not
Okay.
running, not failed, not succeeded, the oldest one that was created, like I just said before, and they update it to running now because suddenly it's running. So the transaction, let me write it down. It would look something like, and again here, my SQL is a little bit rusty, so I hope that I
Yeah.
won't make mistakes. But we would do begin transaction, begin transaction. This is to just say that our worker is starting the transaction, and then here what do? We want to find the oldest based on created at timestamp
Yep.
queued job. So we would
Okay.
do what is it? Select all, so star from our table
Jobs.
is jobs. Yep,
Yeah.
exactly. So from jobs, and here we are looking for we're looking for all the queued jobs. So where status is equal to, so where and here I'll give myself a bit more space, where status is equal to queued, right?
Yeah.
And I forget here if it's one equal or two equals. I'll just go with one. Where status is equal to queued,
Yeah.
and we have to get the oldest one. So to get the oldest one, what does that mean? It means we can order by created at, and we can take only one. So we can order by created at, and limit to 1 and order it either in descending or ascending order, one of the two. So the idea would be
Yeah.
order by, order by, and here you order by, what do we say? Created at. And I think SQL comes with this for free if we're dealing with timestamps, right? So order by created at.
Yeah.
And I guess like you put it in either, like, what's the order? Is it ascending? I think it's ascending. Ascending.
Right, because you're gonna want the smaller number first. So,
yeah.
Yeah.
Exactly, because you're looking for the oldest one, which would be the smallest timestamp. So ascending, and you limit it to 1, and so that would
to
be
get just one record.
Just to get the oldest one, exactly, because there might be multiple.
Yeah.
But you get the oldest one, and then you're not done with the transaction yet. Then once you have that job, you update the table. So here you would actually update the table. So update jobs again. Update jobs, and what do you update? You want to run that job, so you would set the status to, and again here I think you just do set status equal to running, and I think here from this part of the query here where we select the oldest one, we get like one row, right? We can refer to it by an ID, and here it would be something like where ID equals like our ID or something like that. That's, I think, how we would do it. You understand what I'm doing?
Yeah.
Like, I'm just referencing.
Yeah.
Okay.
That makes sense.
And I guess the only thing here that I'm trying to think is, am I missing something?
So a couple things. You forgot to commit, like once you're done with the update. That's essentially going to update that row for the worker. But then what if there are no jobs that are currently in the queue? They're either all running or all succeeded or failed. Where exactly does this come in?
Yeah. So basically, I see. This was, I think, the thing that I was thinking about, and I couldn't put a figure on it. But yes, here, this thing here, because here, this ID, basically, we could not have an ID because we could have not found anything here. And if that were the case, then we would want. So I'm gonna hijack this line here and say that here we would roll back if we don't have a job that is queued and that is the oldest job. So basically, if all jobs are running or succeeded, failed, or there are no jobs, then we roll back the transaction.
Yeah.
And I guess also here, just to point out, we're doing a lot of querying because we are going to be doing this often, and I'll look in a second if this is actually feasible in our database. Yeah, because I'm a little bit scared if this is going to be like too much load on the database. But what I'm thinking is we could actually index this database or this table rather, on the status and on the created at columns. Does that make sense? Just because it'll make things faster.
Yeah.
Okay.
Yeah, sounds good. That would definitely just make this query pretty quick.
Yeah, so I'll put IDX here. Okay.
Cool.
I guess as far as load, I just mentioned the load thing. Like, is this?
Yeah, you did.
So
let's try to figure out if that's reasonable. So these workers, like, when exactly are they executing this dequeue operation?
The workers, they whenever they're building code, they're not doing anything. They are doing something. They're building the code, but they are no longer interacting with a table, right? When they are free, that's when they want to find jobs. Let's assume that we had 100 workers, which is what we said before. But again, I'm not sure if that's actually accurate. So maybe after this or after we finish like the simple design, we can try to estimate how many workers we would have. But if we do have 100, right?
Let's start with that.
Yeah. So with 100, what would they do? Let's say that every 5 seconds they're trying to go to this table and they're trying to perform that transaction, right? That means that per second, you would have 20 of these transactions happening, 20 reads, potentially 20 updates. And that's really in the worst case when they're all like coming in at once. Maybe there are no jobs right now available, no jobs that have been queued, so they keep doing that. That's very handleable for a SQL database. So
yeah, for sure.
okay, yeah.
I really think that's super fine. I do have one question about this.
Okay.
I don't think you've addressed the really bad failure case of
Okay.
say you have a worker that's currently building the code, and power goes off, or it shuts down, or it gets network partitioned.
Okay.
That job will remain in a running state basically forever. You have nothing that's monitoring the running jobs to make sure that they eventually finish.
Yeah.
So
Yeah,
how do you
okay, I
fix
see what
that?
you mean. So you're basically saying like if you have a worker that is currently building code, but something fails not in building the code. Like the building code status didn't necessarily get changed to failed. It's the server, the worker
Exactly.
that died.
Yeah.
Okay. So that is a problem because we don't want
Yeah.
because what would happen, I guess, here you would have a job that would be running perpetually, right?
Yeah.
Okay,
Yeah.
yeah, we don't
And
want
it would just be lost. We don't really know the status because the worker just died in the middle of it. And when you get to a large enough scale, even if we have 100 workers, and say the builds take like 15 minutes,
yeah,
right?
that happens
That's
inevitably.
going to happen pretty frequently. So
Okay.
we need to really take that into account.
Okay. Well, so in that case, the first thing that comes to mind is like some sort of health check that you want to perform, right? You want
Okay.
to like if you mentioned the word monitoring. If you're trying to monitor the status, and here and I'm not talking about the job status. I'm talking about the building status, the worker's status. You want to perform some kind of health check. Now the thing is, who is performing the health check? Like you don't want the workers themselves to be checking up on each other because like what if they all die? What if, half of them die? You're not going to have a stable like this doesn't seem optimal. So I'm actually
Sure.
thinking that you have a fully auxiliary service, like a completely separate service that
Okay.
checks on the servers. So like here, if I scroll back up, here we have our workers. You would have basically like a couple of other servers here that are continuously, checking up on our workers to see like if they're healthy. Does this
Okay.
make sense, like from a high level point of view?
Yeah. Yeah. But so how would that interact with your actual queue? Because those workers or those that auxiliary service needs to somehow change the state of the queue because otherwise the jobs are just stuck, right?
Oh, right. Okay, I see. So you are saying that we could have this auxiliary service here actually. Oh yeah, if there's a job that is running and that is clearly like has been lost
Stuck.
effectively.
Yeah.
Yep. Okay.
Hmm.
Then these would update it. Okay. So then in that case, well, they would still be performing health checks on the servers, but I guess like how do they perform health checks on the servers? Do they could see if they get a response from them, like they continually ping them, or what it could be, but no, because then they don't know necessarily what job it got lost. So what I'm thinking actually
Yeah.
is maybe like the workers continuously send their current health status. They send a heartbeat, like hey, I'm still alive. And this would be
Okay.
done only when you are running code. So when they are not running code, running a job, when they are building code,
Okay.
um, they send a heartbeat. And where would you? I guess you could send the heartbeat to. You could actually like expand the table here. You could have another column that has
Hmm.
last heartbeat and like.
Yeah.
Okay. Yes. Yes. Okay. So the idea is
Let's
this.
do that.
Okay. So I'll expand here with one more column. I'll call it last H. This is last heartbeat, okay? And the idea is
Okay.
this like your workers here, they pop
Yeah.
or they dequeue a job off the queue. They start running code. So when they're not running the job or start not running code, when they're not running the job, they aren't performing these heartbeats or we're not thinking about these health checks. But when they
Okay.
are running a job, they start performing these health checkups by sending heartbeats to the queue. So basically, like they I'll put them like in dotted lines, but they send heartbeats down here to the queue to the jobs table. Let's say, I don't know, we said a job takes how long? 15 minutes on average,
Yeah.
or at most, then every 3 to 5 minutes, and you can change that
Sure.
according to how you want your system. And so they send a last heartbeat, which we store. It's basically an update to the database. You update it in the row of the job that the worker is running. And that's
Okay.
actually really good. And then this service here, let me erase this. We're not actually monitoring the
The
workers.
workers.
You actually
Yeah.
monitor. You continuously pull the jobs table, and you check like, hey, when was the last heartbeat? I guess what do? You get all of the jobs that are running, not the
Yeah.
failed job, not succeeded, not queued. All of the running jobs.
Yeah.
You check the last heartbeat, and you like, how do you know if a job is like lost? I guess it's just if the worker for that job has not sent a heartbeat in past a certain period of time. So basically, like, let's say if the heartbeat is every 3 to 5 minutes, then every 10 minutes, you double the heartbeat, maybe, because you don't want to.
Sure.
You need a margin of error, if that makes sense.
Yeah. Yeah.
But yeah, so
You can't expect the heartbeat to come exactly at the second every time.
yeah, exactly. But so that's how I would do it. And then if we're talking about a SQL transaction or a SQL query that we would write, it would be something along the lines of, like, if you want to, do I have to write it out? Because it would be just select all from jobs where the status is running. You do a little
Yeah.
thing where the last heartbeat is less than, like the current time minus, 2 or 3 heartbeat durations, right? For the margin of error.
Sure.
And
Yeah.
if you found one, then you'll update it back to queued so that it just goes back to the queue. And since it still has
Okay.
the created at timestamp, that's like whatever the original timestamp was, we're good.
Yeah. Yeah. That sounds good. That's exactly what I was looking for.
Okay, cool.
Yeah. So one last thing. Let's try to estimate how many workers we're actually going to be
Okay.
needing here. So I gave some numbers earlier. Thousands of builds, and on average, 15 minutes of build. So how many workers is that going to look like for us?
Yeah, so thousands of builds per day, right? Thousands of deploys, which we said includes builds per day. Can we estimate like 5,000, 10,000? Like,
Yeah, let's say 5,000
okay,
to the middle.
So 5,000 per day. So I'll actually write that down for a second. We'll write it in white. 5,000 builds per day. So builds per day. And we said a worker takes roughly 15 minutes for a build.
Yeah.
So 15 minutes for a build. That's what? That is 4 builds an hour. So there are 24 hours in a day, 96. So let's round it up to 100 builds a day that a single worker could do, right? So 100 builds per day per worker.
Yeah.
And here this is, again, like estimating that every build takes as long as possible, which is roughly 15 minutes. So then we do 5,000 divided by 100. So 5,000 divided by, and we only have 50. So actually, I think the 100 before, the estimation of 100 workers before wasn't actually off the mark.
Yeah.
And
it wasn't. So do keep in mind though that the number 5,000 builds a day, it's not uniformly distributed, right? You're gonna have peaks and valleys there.
Yeah.
So yeah.
Yeah, because thinking back to like past experiences that I've had with code deployment systems, if you're at a large tech company, you're gonna have certain hours of the day, like in the early afternoon Mountain View time, for instance, if we're talking about Google, where you have the majority of the engineers like running submitting code and running builds, or running jobs. So yeah, but I think the point here to make is that this design here is super horizontally scalable. We start with 50 workers on average, but if we need more workers during peak hours, we just add more workers. If we need fewer during off-peak hours, just remove workers. And also, we can even scale this vertically if need be. Like if we can get more powerful machines to have that build time go down from 15 minutes to 10 minutes, then great. But the horizontal scalability is like the key thing here.
Yeah, Okay, so now we have the binary, right?
Yep.
What do you do once the actual like internal build step finishes, that command, that compilation finishes?
Yeah, so the 15 minutes elapse here, roughly speaking, and we
Yeah.
have successfully built the binary. We said that we don't care about the implementation detail of like how to build the binary, how to compile the code, right?
Yeah. Yep.
Okay. And I guess so, sorry, just to super quick tangent because yes, we are getting to the point where we store in our blob store in GCS, which I think I wrote up here. Yep. But just
Okay.
before we get to that, do we have to worry because we are dealing with source code, right? We have the SHA of the commits that we are building, and
Yeah.
we're gonna have to download that source code. Let's say we have 50. No, okay. If we have 50 workers, even 100 workers at once that have to download at every build, like what did we say? Like 100 builds per day per worker. Or 5,000 builds, that's fine.
Yeah.
That's going to be really fast to download the source code. So I'm not
Yeah.
super worried about that.
Yeah. And even if you have a lot of source code, right, like at those really large companies, usually the version control systems will allow you to get incremental patches. So
Okay.
each worker could, for example, clone the entire source code when it comes up, and then just before every build, it just applies the incremental patches.
Okay.
So
Yeah.
that's not all an issue.
Okay. Cool.
Um,
But then
yeah,
to your
but
question that you were asking
yeah,
before, yeah. So sorry for that tangent, but to the first question is like once we're done with that, since we clearly this is no longer a problem, we can store the succeeded build or the succeeded binary into our blob store into GCS. And once
yeah,
that's done, because there might be an issue with the blob store, so we don't want to eagerly update the table. But once it is successfully written to the blob store, then we can update the status to succeeded, and we're done at that point.
yeah. Cool. Yeah,
Cool.
that's exactly what I was looking for. That ordering is actually important. Yeah,
Yeah, waiting for the
you don't want a
right.
successful build to not have been persisted. So
Yes. Yep.
yeah,
Okay, cool. And so I think
cool.
that is the majority of the
So
system.
I do have another question.
Okay.
So I mentioned earlier we have 5 to 10 regions, right?
Yeah.
But you only really mentioned a single blob store or a single bucket of GCS. How does that story change when you take into account the fact that those builds will have to be eventually deployed worldwide?
So let's see, because you're basically saying we don't we might not want to have a single blob store that is catering to all regions because that would be like especially if we've got hundreds of thousands of machines all trying to like download the same file from the blob store, that would be suboptimal, right? Is that what you're
Yeah,
hinting at?
yeah. It's not really feasible for a single blob store in a single region to serve everything.
Yeah, so I think this is where we start to spill into that second part of the system that I mentioned, the deployment system. But I guess it's kind of like the bridge between the building and the deployment
Yeah,
system.
yeah,
So, okay, we have all these regions. I think that, first of all, we should take advantage of the fact that we have these regions because we're catering to a lot of machines globally, but at least we have these regions that we can maybe use to basically split up our system to make it, to have smaller subsystems. So, what I'm thinking is we can actually have regional clusters, like regional
okay,
systems in a sense, regional subsystems that are going to handle the final part of deployment. And the idea with that is that if we have regional clusters, we could have actually regional buckets, like regional GCS buckets, which are basically the idea is like you replicate the binary that you have in your main, blob store here. You replicate it
yeah,
across all of the regions that have their own special, blob store or bucket that's catering to them, and then you have a better system from that point of view. Does that make sense?
yeah. Because you would be like if we have 10 regions, you'd be replicating that build 10 times
Yep.
to the 10 regions, and then these regional buckets would serve their own regions
Exactly.
with their hundreds of thousands of machines. Yep.
Exactly. So just to draw it out, the idea would be you have one, two, three. Let's go with five for now. Four,
Yeah. Sure.
five 5 regions. These are all the regional buckets or regional blob stores, whatever you want to call them. And I guess, let me think though. We said here we only want to update the table when the write to the main blob store like succeeds. I don't think we need to do that for the others. In other words, like we don't want workers to be blocked because of replicating data from this blob store to all the other regional buckets. So what I'm thinking is the write to the main blob store succeeds. The worker is released, so to speak. The worker can update the table and then go back to running another job. And then we have some asynchronous replication here between this main blob store and all of the regional buckets. Does that make sense?
Yeah. That sounds like it would work.
Okay, cool. So then, that's what I would do. And then I am thinking that, once you start to get ready for the deployment system. And so here, are you okay if I move forward with the deployment system?
So there is one more thing, I guess a requirement I didn't mention before, but we'd like to only allow deployments of builds that have already been replicated everywhere, or to all of these regional buckets. How would you enforce that? How do you actually figure out? How do you keep track of which region has, or which build is already replicated and which one isn't yet?
Is the idea behind that if you have some kind of like internal UI user interface where an engineer can deploy a build, they press a button and deploy build, you want that build to actually be deployable to all the regions if they're all relying on their regional bucket. Is that the idea?
Yep.
Okay.
Yeah.
Also, this is where maybe now I'm having second thoughts. Like maybe it does make sense to have our workers, wait for all the, but no, because then our workers get stuck. Like we want this part of the system to be optimized. We don't want our workers.
Yeah. What you have, we don't want our workers we don't want our workers to be in charge of like the replication status, so to speak, of the build. I feel like a separate system might work better for that.
Okay, yeah, so that's what I was going to get at. Then it would be some sort of like we can just have a completely separate service. I'll write it maybe like in blue here, blue rectangle to really differentiate it. And this service basically checks the replication status of a binary. So like this service basically pulls the main blob store and says, hey, I see a new binary in there. Let me check continuously all of the regional buckets, see if they have that binary. And until they do, that binary is not ready to be deployed, or that build is not ready to be deployed. But once I've aggregated the binaries or seen rather that the binary has been replicated across all regions, then we're ready. The build is deployable. So this would basically be pulling all of the regional buckets, and it would be storing in a database. So maybe I'll give myself a bit more space. Let me actually move this here. Move this a little bit to the left here. Erase this. Here you would have a database down here. And this database would be, you would have the build ID or the build name. And I guess the build name, we had it here, right? This is the build name. So this would be the build name. So I'll put BN. And then here, sorry, I'm running out of space on my screen here, but here you would have the replication status. So I'll call this just S for status, and this replication status would be synonymous with like is deployable. Does that make sense?
Okay. Yeah, cool.
And so
we can know, so the user, the engineer, or the UI can know whether a build is actually deployable because it was replicated or not.
Exactly, and then the UI can, depending on how you want to build that UI, the UI can literally rely on an API that uses this database, and the UI can either show just builds that are deployable, or it can show all builds and gray out the ones that aren't deployable yet. You can do this however you want from there.
Yeah, cool. That sounds good. I like that. So I think we can move on to. I know you're eager to. We can move on to how things actually get deployed.
Yeah, because I started talking about that a second ago. So let's see. An engineer presses a button, right? They press a button, and again, thinking back to experiences I've had with code deployment systems, sometimes you will have a button that literally allows you to deploy a build. What happens there? You suddenly want in basically less than 20 minutes, because we said the build takes 15 minutes, the replication here takes 5 minutes maybe. So in about 10 minutes, you want that build, which is essentially a 10 gigabyte file, to be replicated, or not replicated, to be downloaded, to be spread to hundreds of thousands. So we're maybe entering millions of machines if we've got 10 regions. So we can't just do like a naive thing where the machines, the hundreds of machines, even if we've divided our regional clusters with their own buckets that serve the machines, you can't have 100 machines downloading one by one a 10 gigabyte file, even on the best network speeds.
100,000 machines, you mean? Yeah.
100,000 machines.
That's,
So
it seems unreasonable.
It seems unreasonable. So I guess my thought here is that this seems to lend itself perfectly to a peer-to-peer network where you have the machines, like of your hundreds of thousands of machines, they all pertain to a region, right? They are all sort of part of a regional cluster, and all of the machines in one regional cluster are peers in a peer-to-peer network, and through the peer-to-peer network, they can actually download this 10 gigabyte binary or these multiple 10 gigabyte binaries repeatedly throughout the day very fast. This will speed up our system much faster, and we'll actually be able to reach that 30-minute mark. Does that?
Yeah. Peer-to-peer is exactly the right solution here. And it is how large companies end up doing it.
Okay.
But so now, can you walk me through what happens when an engineer presses, the deploy build B1? Let's say there's a build called B1. Deploy B1 globally. What exactly happens that triggers all of these machines in those clusters to download the binary and run it?
Yeah, okay. So because just so that I get a clear sense of what's going on, I'm going to just add a few things to this design here, or to the drawing of the design.
Okay.
For each regional cluster, right, and I'm grouping them by these buckets here, these regional buckets.
Yeah.
We've got a bunch of machines, and these are going to be peers in some peer-to-peer network, right? Now you've got some engineer in, let's say, Mountain View, the West Coast, or wherever in your company that's pressing a button on the UI. So let's say the UI is here. This is the button that they press, and maybe this goes to a server that kind of like triggers everything. So maybe this is some server that triggers the whole deployment.
Yep.
You suddenly want all of these peers to know that they can start downloading a binary, as part of a peer-to-peer network. And here, if you have, you're going to want to be able to do this repeatedly, right? You might have an engineer who presses a button to start a deployment, and then another engineer who immediately presses another button to start another deployment, right? Because you might have multiple builds, one after the other. I'm thinking what might make the most sense here is a structure or a design where you have a single, at any given point in time, you have a target build. You have a kind of a goal state, right? Where you say,
okay,
I press build B1 to deploy. Build B1 is now the target state. It is now the target build. And if
the goal state,
the goal state, yes. And if a peer in the peer-to-peer network or a machine sees that, they immediately say, okay, I have a new goal state. This is not the current build that I'm running or that I've downloaded last or whatever, so I need to start downloading it from the peer-to-peer network. The only thing is here, again, do we want this to happen? This can't happen. Since we've been taking advantage of this whole regional architecture, we don't want this goal state to only live on one server, here globally. So I think we should make use of the regional architecture that we've designed and design it using that. So the idea would be, engineer presses a button, right?
Yeah.
This updates the goal state, and updating the goal state.
Where do you keep the goal state? Yeah.
Let's see. We're talking literally a key value pair here, right? It's a current build B1. So I think we can have, actually, our system probably has some configuration in place, right? So our system here probably has, we can have a key value store that stores just configuration for our system as a whole, or parts of our system. And here, one of the configuration parameters would be the build version. So here we can have a key value store like etcd or Zookeeper that stores our configuration. So I'll write it, I'll write it in blue to represent the key value store. And here you have build version b_v for build version, which points to, let's say, b1. And if the engineer presses another button for b2, then this gets updated to b2. But then the idea, just as I just mentioned about like taking advantage of the regional stuff, is how do you do this? Yeah, you probably have a key value store at the regional level. So every I'll mark this with KV or KVS for key value store. So I'll put KVS. Okay. Every region has a KVS, and these KVSs are actually pulling the global key value store, and they watch for changes to BV, B1. You know, like here, let's say they're all on build B1, and suddenly this gets updated to B2, right?
Yeah.
They are all pulling this key value store. So they're all pulling, let's say, every 5 seconds or every 1 minute or whatever. And they see, oh, there's been a change. So they update themselves to now have build B2. And then all of the peers at the regional level, or all of the machines, the end machines, the target machines, they, when they've finished downloading a build, when they're kind of like at steady state, so to speak, they pull their own regional KV store, and they look if the KV store holds a build that's different than the one that they're currently running or that they've last downloaded or what have you. If they see a change, then they start the peer-to-peer network, or that's unidiomatic. They start downloading the file, the binary, through the peer-to-peer network, and there you go. That can be done like repeatedly throughout the day.
Yeah. So this turns out this is actually pretty close to how it works in a real large-scale system. So so yeah, this is great.
Awesome. And like I said before, I do think that I'm pretty satisfied with this design because I think that it's scalable and it's kind of flexible. Like here with our workers, we said it was very horizontally scalable. I'm sure that here we can take advantage even further of our regional architecture. So yeah.
Yep. Yeah, exactly. No, this is definitely great. Thanks, Clement.
Okay. Awesome. Thank you so much. With that, I hope that you found this video informative, and we'll see you in the next one.